My name is Josh Priest, and I worked with Ravi and Madhav on solving decision problems for synchronous dynamical systems using Boolean satisfiability. So your first question probably is, what is a synchronous dynamical system? At its base, a synchronous dynamical system, which I'll refer to as a SIDS, is an undirected graph with each node having a Boolean state of 0 or 1 assigned to it. Each node has a local function that determines how the state will change in the next time iteration based on its inputs. So every single node will take in its current inputs at one time, and then all will change synchronously. So these SIDSs have some interesting problems that generate out of them. One of them is a fixed point problem. What this problem asks is if there is a configuration that is its own successor. So if this is the case, that configuration is a stable state of the SIDS, and it won't change out of that state. Another problem is the configuration sequence completion problem. So given a trajectory for the SIDS with some unknown values, what this question asks is there a way that we can assign Boolean states to the unknown values such that it represents an actual trajectory of the SIDS? So these questions can be answered by exhaustively calculating every single configuration that could exist for a SIDS, but that's extremely computationally expensive, and it will take a long time, and it isn't really feasible on large graphs. So what we can do instead is all of these problems can be converted into what we call a Boolean satisfiability problem, otherwise known as SAT. So the nice thing about SAT is will return answers to these problems of whether they're satisfiable or not. So it'll return whether there is an answer to the problem. And there exists lots of open source software out there that solve these problems very quickly. So there's a few popular open source SAT solvers that can take in thousands, millions of clauses for these problems and produce solutions very quickly. So I wrote a Python program that takes in a synchronous dynamical system and a problem, converts it to a SAT problem, and then feeds that to a SAT solver and gets a solution. So these are some of the results for the fixed point problems. You would expect that certain functions would take longer than others, and we didn't really see that in our results. A lot of these look to be exponential according to the number of nodes, but it's hard to say because we don't have enough data. So I don't want to make any assumptions about the actual function of both the time it takes to convert and or solve these problems, or how big the actual Boolean satisfiability problems generated are. The CSC problems had similar results, but so SAT solvers, when they're given an unsatisfiable formula, will return the result very quickly. They'll decide that the problem does not have a solution and will return that in less than a second. So we have data for about nodes of 1,000, or graphs of 1,000 nodes, but we've recently been able to kind of extend that out, and these problems might take a while to run, but we can get more data sets. So part of what we want to do in the future is expand these experiments up to significantly higher numbers of nodes and edge densities, such that we can kind of generate more data and see some patterns in how long these take. We want to discover some trends of how different SIDSs and SIDS problems can affect these SAT problems that are generated, and how long they'll take to solve. And then at the end of this, we want to provide this program that converts SIDS problems to SATs as a free and open source program to the community.